All right, Epsilon Delta proofs day 2. Let's review what that absolute value inequality means. Yesterday, or the previous lesson, we were looking at um, choosing an x, or looking at the x's that are within delta of 4. So we go up delta and down delta, and another way to represent that is the absolute value of x minus 4. The x is any x in here. If we do x minus 4, then this is saying that the absolute value of that is the distance away from 4 is less than delta. And look what happens if we rewrite this as a compound inequality, put the negative delta, and add 4. And now we see that this means all the x's that are between delta plus 4 and 4 minus delta. 4 plus delta, 4 minus delta. All the x values between these 2 points. Now, if we, and that just shows that the absolute values, we don't have to have absolute value. We could just have an inequality like this. And let's look at a limit. If we have the limit as x goes to 0 from the right, radical x equals 0. Prove that. And we should remember that radical x looks like this. And we are only looking at x values from the right. So in this case, we won't have to worry about the absolute value. And our preparation is if 0 is less than x minus 0 is less than delta. I'm just following the format from the previous lesson. We would always do x minus that number. It's 0. We wouldn't have to write the 0, but it's the same format. Then f of x minus the limit is less than epsilon. So now we can simplify that. Radical x is less than epsilon, and we can say that x is less than epsilon squared. So we choose delta to be epsilon squared. Then our statement is, given epsilon greater than 0, let delta equal epsilon squared. If 0 is less than x minus 0 is less than delta, I'm just copying the same format. We could just write x. Then radical x minus 0 is less than, x is less than delta, so radical x is less than radical delta, which equals square root epsilon squared. Because we chose delta to be epsilon squared, we substitute, and then we finish the statement. And that's the end. We showed that we chose a delta that makes f of x minus L less than epsilon. And the focus of today's lesson is dealing with quadratic functions. Let's prove the limit of x squared equals 9 as x goes to 3. So our preparation is, if 0 is less than x minus 3 is less than delta, then x squared minus 9 is less than epsilon. And now we work with this, because our goal, like we saw in the previous lesson, we need to have x minus 3 showing up in here. And there it is, x minus 3, but it is with an x plus 3. So let's do some work over here, and we want the x minus 3 to stay. So here's what we do. Let's let -1 less than x minus 3 is less than 1. And every example we do today, we're going to just choose this to be 1. And it's just picking something that's easy, standard. We're going to choose the distance of x away from 3 is going to be less than 1. Then we find out what x is. Let's add 3, and then we need to find out what this is going to be. How can we characterize x plus 3? So we want to see what x plus 3 equals, and that's going to be 4 plus 3. If I add 3 here, add 3 here, add 3 there. And now we can say that x plus 3 is going to be less than 7. So another way that this is written, we could say that just let x plus 3 be c, and then we know that x plus 3 is less than 7, so that means this is, let's just make that a 7, and x minus 3 would be less than epsilon over 7, and we'll choose delta to be epsilon over 7. Alright, so we want the x minus 3 to stay there, but based on x minus 3, we find out that x is between 2 and 4, and then x plus 3 is between 5 and 7. So we know that x plus 3 is less than 7. We can say that this absolute value is less than some number times x minus 3, where we just create a boundary for x plus 3. X plus 3 will always be less than c, and we know that we want to make that be 7 based on what we saw here. Now that gives us a delta to choose. And this is the same format as the previous lesson. We have f of x minus L, which equals x plus 3, x minus 3, it's less than 7, x minus 3, and x minus 3 is less than delta, which is less than 7 delta, which equals 7 epsilon over 7, which equals epsilon. Let's skip that one. We're going to do this one. All right, and pause the video and try that one. X minus 2. 0 is less than x minus 2 is less than delta. Then f of x minus L is less than epsilon. And here we have that, and we factor, and then we need to keep x minus 2. We want to keep the x minus 2, and based on, oops, this should be a minus 2 also. Let's choose x minus 2 between 1 and negative 1. And that gives us, here we just have to go ahead and say that x minus 2 is less than 1. And we'll have 1 x minus 2 is less than epsilon. X minus 2 is less than epsilon. And we can just choose delta equals epsilon. Zero is less than epsilon. X minus 2 is less than delta. Then f of x minus L, which equals x squared minus 4x plus 4, which equals x minus 2 and we know that x minus 2 is less than delta, so we can say that this is less than delta x minus 2, and delta is less, delta equals epsilon. No, x minus 2 is less than 1. So we have to do, let's see, we could say that, but we can also say this is less than delta times 1, because that's less than 1. We made it be, chose it to be less than 1 up there. So we replace one of these with a delta, replace one of these with a 1, and then we get delta equals epsilon. Alright, pause the video and try that one. So, our preliminary work is to say that x minus negative 2 is less than delta, then f of x minus L is less than epsilon. And we want to keep the x minus 2. We want the x plus 2 because that's a negative. We're looking for x minus negative 2, which is x minus negative 2 there. That means we don't want that. We want to replace that. And so we're going to take this and base everything off of that. X minus negative 2 or x plus 2 is less than 1. So that's negative 1 is less than x plus 2. So we're just using x plus 2 and saying that it's less than 1. And then we subtract 2, subtract 2. We need to replace the x minus 2. So we'll subtract 2 from all of these. Negative 1 minus 2. And negative 3 minus 2. Alright, now this, we have to be careful here that, and we're going to say that when we rewrite this, we'd want to say that 3 is less than, x minus 2 is less than 5 if we're looking at positives. Because 5, we're just looking at the distance, we're looking at distance, so the negative doesn't matter. We need to take absolute value, so we wouldn't want to say that x minus 2 is less than 3 since it's between negative 3 and negative 5. We want to say that x minus 2 is less than 5, not 3. And that lets us say that the x minus 2 will be less than 5. So we can say 5x plus 2 is less than epsilon. X plus 2 is less than epsilon over 5. And that lets us choose a delta. Choose delta equal to epsilon over 5. So this is f of x minus 3, which equals x squared minus 4, which equals x plus 2, x minus 2, and we're going to say that the x minus 2 is less than 5. So we can say this is less than 5x plus 2. And we know that x plus 2 is less than delta. This is less than 5 delta. And delta equals epsilon over 5, which equals epsilon. Alright, so this is the step that is required for quadratic functions, proving limits of quadratic functions, where we have the two factors, and we'll just say that the factor that we want to use is going to be less than 1. We just say, we know we're dealing with small numbers, but let's just choose 1, and we're going to start there and go less than 1. Then we get to an x. We want a bound for the thing that we need to get rid of. So now we put this x minus 2. We change this into an x minus 2 by subtracting 2. And now we can see that x minus 2 is going to be bounded by 5. And we can replace the x minus 2 with a 5 and say that then that has to be less than epsilon. All right, and we'll stop there.